Every year, workers are killed or permanently disabled by machines that weren't supposed to be running. Crushed hands, lost arms, electrocutions, and almost every single one of those tragedies had one thing in common: the energy wasn't properly controlled. Today, you're going to learn exactly how to make sure that never happens to you. OSHA's Control of Hazardous Energy standard, known as Lockout Tagout, exists for one reason: to protect you. It covers over 3 million workers across the United States. Failing to follow it is one of the most frequently cited OSHA violations year after year. This isn't bureaucratic box checking. This is life and death. This training is delivered in two parts. Part 1, which you're watching now, covers the OSHA standard, your roles and responsibilities, and a deep dive into every type of hazardous energy and how to control it. Part 2 covers the complete step-by-step lockout tagout procedure, group lockout, the minor servicing exception, inspections, and your legal rights. Together, they meet all requirements for authorized employee training under 29 CFR 1910.147. This training is specifically designed for authorized employees, someone trained to apply lockout or tagout devices to control hazardous energy before performing service or maintenance on machines and equipment. By the end of both parts, you'll know exactly what to do, when to do it, and how to prove you did it right. Lockout/tagout is governed by OSHA Standard 29, CFR 1910.147, the Control of Hazardous Energy standard. This standard applies to general industry and covers the servicing and maintenance of machines and equipment where unexpected energization, startup, or release of stored energy could harm workers. It is the legal foundation for everything you'll learn in this training. You might think, can't I just turn the machine off? Here's the problem. Turning a machine off doesn't eliminate the energy. A capacitor can still hold an electrical charge. A hydraulic line can still hold pressure. A spring can still be loaded. Switching something off gives you a false sense of security. Lockout tagout requires you to actually isolate, control, and verify that the energy is gone. The standard applies when employees perform service or maintenance activities, setting up, adjusting, inspecting, lubricating, or cleaning equipment where contact with unexpected moving parts or energy release is possible. It applies broadly across general industry. Knowing what falls under this standard is the first step toward knowing when full lockout procedures are required. The standard does not apply to cord and plug connected equipment where the plug is under the exclusive control of the employee performing the work. It also has carve-outs for minor tool changes and routine adjustments integral to normal production, with very specific conditions. And we will cover both of those in thorough detail shortly. Knowing the boundaries matters just as much as knowing the rules. Quick check before we move on. Pause and think about this. A worker turns off the power switch on a conveyor belt before reaching in to clear a jam. Is that worker protected? Yes or no, and why? The answer is no. Turning off a switch doesn't verify or isolate the energy. The worker must use a proper lockout procedure, apply a lock, and verify zero energy state. Simply switching off is not lockout. That's exactly what we're going to teach you how to do right. OSHA defines 3 distinct roles in any lockout program. The authorized employee is trained to lock out equipment. That's most likely you. The affected employee works in an area where lockout tagout is being performed, but doesn't personally apply locks. The other employee is everyone else who needs to understand not to touch locked out equipment. Each role carries specific responsibilities. As an authorized employee, your responsibilities are clear and non-negotiable. You must know the energy sources on every piece of equipment you service. You must follow your facility's written lockout procedures. You must apply your personal lock, no one else's. You must verify zero energy state before work begins. And you must remove your lock only when work is complete and the area is safe. Affected employees have a simple but critical responsibility. Do not attempt to restart or re-energize equipment that has been locked or tagged out. When you see a lock or tag on a machine, stay out and notify your supervisor. You are never authorized to remove someone else's lock, not even if you think the work is done. Only the person who applied it can remove it. Your employer has obligations too. They must develop a written energy control program, create specific written procedures for each piece of equipment with multiple or complex energy sources, provide training and retraining when necessary, and conduct periodic inspections, at least annually, of every energy control procedure. Your facility's Lockout Tagout program is only as good as its written foundation. Your lockout hardware must meet OSHA requirements. Padlocks must be individually keyed. Only you hold the key. Lockout tags must state that the equipment may not be operated, must be standardized in color, shape, or size, and must be strong enough to prevent accidental removal. OSHA requires a minimum 50-pound pull strength. Your lock is your life. Treat it as something irreplaceable, because in a sense, it is. Before you can control hazardous energy, you have to recognize it, in every form it takes. Workers have died because they controlled the obvious electrical source and missed the hydraulic lines still under 3,000 pounds per square inch, or the spring still loaded under full tension. Every energy type has a unique signature, a unique way it injures, and a specific method to control it. Let's go through every single one. Electrical energy is the most commonly encountered hazardous energy in industrial settings. It exists in motors, control panels, wiring, capacitors, and battery systems. It can be AC or DC, and it doesn't require direct contact to injure. Arc flash events can release explosive energy across distances, generating temperatures exceeding 35,000 degrees Fahrenheit, nearly 4 times the surface temperature of the sun. Electrical energy injures in 4 distinct ways. Electric shock. Current passing through the body can cause cardiac arrest, respiratory failure, nerve damage, and severe burns even at relatively low voltages. Arc flash causes third-degree burns and blindness. Arc blast. The pressure wave from an arc flash event can throw workers across a room. And electrical fires can trap or burn workers at a distance. Remember, it's not the volts that kill, it's the amps. Controlling electrical energy requires isolating it at the source and verifying zero state. Primary lockout devices include clamshell circuit breaker lockouts that enclose the breaker and accept a padlock, electrical disconnect lockouts for knife switch disconnects and pull-out fuse blocks, and plug lockouts for smaller cord-connected equipment. After isolating, you must test with a calibrated non-contact voltage tester. For high-voltage systems, test before touch procedures and proper PPE are mandatory. Hydraulic energy is pressurized fluid, typically oil, used to transmit force in cylinders, lifts, presses, and clamping systems. Industrial hydraulic systems routinely operate at 1,000 to 5,000 pounds per square inch. At that pressure, a pinhole leak can inject fluid directly through the skin, called hydraulic injection injury, which looks deceptively minor on the surface but can cause tissue destruction, gangrene, and amputation if not treated within hours. Controlling hydraulic energy requires 3 specific steps. First, isolate the hydraulic supply using a lockable valve. Ball valves or gate valves fitted with a valve lockout device and your personal padlock. Second, release residual pressure by opening a bleed port and confirming the gauge reads 0. Third, and critically, if any component is supported by hydraulic pressure, mechanically block it before work begins. Never rely on hydraulic pressure to hold a load during maintenance. Pneumatic energy is compressed air or gas powering cylinders, actuators, and pneumatic tools. These systems typically operate between 80 and 150 pounds per square inch, more than enough to rupture tissue, inject air into the bloodstream, causing a fatal air embolism, propel debris at lethal velocity, or rupture eardrums. A pneumatic cylinder can extend with hundreds of pounds of force with zero warning after isolation if pressure hasn't been properly exhausted. Controlling pneumatic energy requires isolating the air supply and exhausting trapped pressure. Lock a pneumatic ball valve or air supply valve using a valve lockout device and your padlock. Then, exhaust downstream pressure through a manual bleed valve until confirmed at zero by a pressure gauge. Finally, for pneumatic cylinders, gravity can still move a cylinder after pressure is exhausted if a load is involved. Mechanically block any cylinder that supports a load. Mechanical energy includes stored energy in springs, flywheels, counterweights, elevated components, and anything held against gravity. A loaded spring can release fast enough to sever a finger or fracture bone. A flywheel can continue rotating for minutes after power is removed. An elevated machine component, a die, a press head, a suspended platform, contains gravitational potential energy that can crush anyone beneath it the moment its support is removed or fails. Controlling mechanical energy requires physical intervention. You cannot simply turn it off. Springs must be detensioned and secured in a safe position. Flywheels must be allowed to come to a complete stop, confirmed, not assumed, with braking mechanisms applied if available. Elevated components must be lowered to a rest position or blocked using specifically rated blocking devices or safety props. Never use improvised supports like wood blocks unless they are rated and specified by your written procedure. Thermal energy exists in steam lines, heated process equipment, ovens, boilers, hot liquids, and cryogenic systems. Steam is particularly severe. A steam line at 300 degrees Fahrenheit and 150 PS, I can deliver third-degree burns in under a second of contact. Cryogenic materials present the opposite hazard. Contact causes freeze burns and tissue destruction, while rapidly expanding cryogenic gases can displace oxygen in a confined space, causing asphyxiation without warning. Thermal energy control starts with isolation and then requires something that workers frequently skip: time. For hot systems, isolate the heat source, then allow the system to cool to a safe working temperature confirmed by a calibrated thermometer, not a touch test. For steam lines, isolate the supply valve, lock it out, drain the line, and confirm zero pressure and safe temperature. For cryogenic systems, isolate supply valves, purge lines with inert gas, and confirm safety with appropriate atmospheric monitoring equipment. Chemical energy in the lockout context refers to the hazardous potential of pressurized chemical lines, reactive materials in piping systems, and chemical processes that can spontaneously release energy. Injuries include chemical burns from corrosive materials, toxic inhalation from released gases or vapors, explosion from reactive materials under pressure, and asphyxiation from oxygen displacement in systems purged with inert gas. Chemical energy is often invisible, making it uniquely dangerous. Chemical energy control involves isolating chemical supply lines using lockable valves, depressurizing and draining lines before any work, and purging the system with inert gas or water flush as appropriate for the specific chemical involved. For high-hazard chemical lines, a double block and bleed configuration is commonly required. 2 isolation valves with a bleed valve between them, confirming true isolation. Always don chemical-resistant PPE and confirm safe atmospheric conditions with air monitoring equipment before opening any chemical line. Gravitational energy deserves its own spotlight because workers consistently underestimate it. Any elevated component, a machine arm, a die set, a conveyor section, a vehicle lift, contains stored gravitational potential energy that will release downward the moment its support fails or is removed. Workers are crushed every year by components assumed to be safely held by hydraulics or mechanical stops that were never designed as a maintenance safety support. If it's above you, block it, period. You're preparing to service a large industrial press. You've identified electrical power as the primary energy source and have locked out the main breaker. Before you reach into the machine, what else must you consider? Think about what other energy forms we just covered that might be present in a hydraulic press system. The correct answer is B, and this is exactly why the identification step is so critical. A hydraulic press can have electrical energy, hydraulic pressure in the cylinders and lines, mechanical energy in springs or linkages, and gravitational energy from the elevated ram itself. Every single one must be identified, isolated, and controlled. Missing any one of them can be fatal. OSHA's Lockout Tagout standard contains a specific exception for cord and plug connected equipment. If the equipment is connected by a cord and the plug is under the exclusive personal control of the employee performing the service or maintenance, full lockout tagout procedures are not required. But the word exclusive is doing enormous work in that sentence. Let's break down exactly what it means and where the boundaries are. Exclusive control means you have the plug in your physical possession, or the plug is unplugged and secured in a way where only you can access it. If you unplug a machine and set the plug on the floor 3 feet from the outlet, that is not exclusive control. Someone can walk by and plug it back in without realizing you're working on it. The plug must be physically with you, or secured using a plug lockout device that only you control. When the plug can't stay in your hand because you need both hands for the work, a plug lockout device should be used. Plug lockouts are enclosures that fit over the plug head and accept a padlock, physically preventing the plug from being inserted into any outlet. They come in multiple sizes: standard 120 volt, 240 volt, 277 volt, and industrial multi-pin configurations. Like all personal lockout devices, only your padlock goes on it. This is your control point. The cord and plug exception fails immediately in several situations. First, if the equipment has multiple power sources. Some industrial equipment has both a cord and plug for controls and a hardwired motor, or 2 separate cords. Unplugging one does not control the other. You must identify and control every source. If any energy source cannot be controlled by a plug under your exclusive control, full lockout procedures are required for that source. Unplugging a cord and plug device does not eliminate stored energy remaining inside the equipment. A large motor may continue to spin after unplugging. Coast downtime. A capacitor in the equipment may remain charged. A pneumatic system built into a cord and plug machine may retain pressure. The cord and plug exception addresses electrical energy from the supply line only. It does not automatically address other forms of stored energy within the equipment. You must assess and control all residual energy separately. The cord and plug exception only provides protection when your control of the plug is genuinely exclusive and uninterrupted. High traffic areas, multiple workers in the same space, shift changes, and shared equipment all increase the risk that exclusive control is compromised. If there is any realistic scenario where someone could plug the equipment back in before your work is complete, the exception doesn't provide adequate protection, and a plug lockout device is required. For any cord and plug equipment where work takes more than a few minutes, both hands are needed, or the environment is shared, use a plug lockout device with your personal padlock. This gives you the flexibility of the cord and plug approach, while adding the physical security of a lockout device. You can never be overprotected. You can absolutely be underprotected. Build the habit of using a plug lockout. Make it automatic. Cord and plug scenario. A maintenance tech unplugs a bench grinder to replace the grinding wheel. The grinder is on a shared workbench in a busy shop, and the tech sets the plug on the bench beside the machine. Is the cord and plug exception being applied correctly? What should the tech do differently? Answer B. Placing the plug on the bench is not exclusive control. Anyone can pick it up and plug it back in. The tech should hold the plug personally or, best practice in a shared space, use a plug lockout device with their personal padlock. Being unplugged is only the first step, not the complete procedure. And if that grinder has any stored mechanical or electrical energy, those must be assessed too. Let's quickly review what you've covered in Part 1. You now understand OSHA's 29 CFR 1910.147 standard and who it applies to. You know the 3 lockout roles and your responsibilities as an authorized employee. You can identify all 6 types of hazardous energy, understand how each one injures, and know the specific lockout methods for each. And you understand the cord and plug exception, including exactly when it does and doesn't apply. In Part 2, you'll learn the complete 6-step lockout tagout procedure, step by step, with nothing left out. You'll cover group lockout for multi-worker situations, how to restore equipment to service safely, the minor servicing exception in full detail, annual inspection requirements, training documentation, and your legal rights as a worker. Part 2 is where knowledge becomes procedure, and procedure becomes protection. Before you move to Part 2, make sure you can answer these questions from memory. Name the 6 types of hazardous energy. What does exclusive control mean in a cord and plug situation? What are your 3 key responsibilities as an authorized employee? If you can answer all 3 confidently, you're ready for Part 2. If not, review the sections that need reinforcement. Part 2 builds directly on what you've just learned.